So before taking the break, we discussed about different intra-domain routing protocols. So the protocol that you can use to forward a packet within an autonomous system, and there we have used this CIDR concept along with the link cost to form a routing table and using that routing table to forward the packet. Now let us see that how we forward the packets from one autonomous system to another autonomous system. Now, routing between two autonomous systems, we call them as the routing domains. Okay. So typically, these autonomous systems, they use a pre-configured routing protocol depending on the protocol that is being configured by the network administrator of that particular autonomous system. So that's why we call an autonomous systems from the routing perspective, we also call it as a routing domain. So the routing between two autonomous systems, we call them the exterior gateway protocol or the EGP. Now, we can have three different types of autonomous systems. Multi-homed autonomous systems. The multi-homed autonomous system has connection to more than one autonomous system. The stub autonomous system. The stub autonomous system means it is connected to only one or other autonomous system. And the transit autonomous system, that means it basically provides the transit connection between two different autonomous systems. Okay. So here is an example about we'll discuss about this three different kind of autonomous systems in details. Like so, typically in a multi-hop autonomous systems, it is the internet service providers or typically Tier 2 or Tier 1 internet service providers who are connected with multiple other autonomous systems. The stub autonomous systems are basically the point of presence or the users who are getting the services. Well, so they just consume the data and they do not forward it to the other autonomous system that we call the stub autonomous systems. And then the transit autonomous system, these are the kind of special type of autonomous systems. They do not consume any data traffic or produce any data traffic, rather they forward the data from one autonomous system to another. Okay. Now, each autonomous system can run its own inter-domain routing protocol, as I was mentioning. Okay, so we call them as the interior gateway protocol, like the OSPF, RIP, all these different kind of protocols. They can even use a static routing or a mixed of different routing at different subnets. So it might also happen that if our CIC wants, they can use one particular routing protocol within one subnet and another routing protocol in a different subnet. Okay, so that is entirely based on the configuration planning or configuration policy of the network administrator. Now, in case of this inter-domain routing protocol, the main issue is that the autonomous systems basically share something called the reachability information. So later on, we'll see in details that what is meant by reachability information. So broadly, this reachability information is a description of the set of IP addresses that can be reached via given ACE. Okay. So we basically say that, well, these particular autonomous systems can be used to forward the packet to this set of IP addresses. And the set of IP addresses in CIDR notation, you already know that they are represented in the form of a subnet. Okay. So it basically says that, well, in this particular subnet, you can forward the packet if you can reach to this autonomous system. Well, now the challenge here is that each autonomous system has to determine its own routing policies, and the routing policies for an autonomous systems might be very complex. So, for example, a routing policy for an autonomous systems can be something like this: that whenever possible, I prefer to send traffic via ASX than via AXY. But I will use ASY if it is the only path, and I never want to carry traffic from ASX to ASY or vice versa. Okay. So this kind of complex information or the complex routing policy can be there. So what does it mean? What does this particular policy means? Okay. So let us see these three classes of traffic that we might have. So I have three different autonomous systems here: ASX, ASY, and ASZ. Now here you see that ASZ is a kind of multi-home AS. Well, it has connection with ASX and ASY, where ASX and ASY are the stub base. Well, so that means ASX is just connected with ASJ and not forwarding traffic to any other autonomous system. Similarly, ASY is a stub base. It is getting the traffic from ASJ and not forwarding to any other AS. Now this particular routing policy basically says that I prefer to send traffic via ASX than via ASY. Okay, so that means from ASJ, my primary path will be towards ASX. Okay, so if I want to forward any traffic, I will forward it to ASX, and I will use ASY if it is the only path. That means if somehow this gateway router is not working, that means my primary path is broken, then only I will use the path towards ASY. But I never want to carry traffic from ASX to ASY or vice versa. That means if certain traffic is originated in ASX and destined for ASY, well, so that means the traffic is not originated from a machine or not destined from a machine which is within ASJ. So this kind of traffic is called a transit traffic. Okay, so that means this ASJ, this voluntarily carrying the traffic of ASX and forwarding it to ASY. And the policy is that I do not want such kind of transit traffic to be forwarded, and that can be a policy for an autonomous systems or an internet service provider, right, based on their business policies. So, for example, the Airtel might have an agreement with BSNL, and it might agree that, well, I will forward the packets from BSNL. But say Airtel doesn't have any agreement with Jio, and Airtel doesn't want to forward any packet from Jio. So if you are a Jio subscriber, maybe Jio network need to find out another part based on their own subscription policy. So this entire routing policies between different autonomous systems, it is not precisely a kind of shortest path routing or the least cost routing. Well, so the main complexity of inter-domain routing protocol is to adherence to this kind of policies, which are mostly kind of business policy, and the policies that are being set up based on the cooperation or the peering relationship between different kind of network service providers. Okay, so that is why many people or many engineers, they do not call these inter-domain routing protocols as the routing protocols. Rather, they call it as the kind of packet forwarding protocol or the kind of peering protocols. Okay. So it is basically to forward the packet from one AS to another AS, depending on its routing policies or its business policies that it has set up by setting up the peering relationships with other autonomous systems or other internet service providers in the internet. Okay, so that way these kind of protocols are much more complex compared to the kind of protocol that we have already studied, like OSPF or RIP, where my major objective is to reduce the path cost. But here we see that we need to adhere to these policies, which are kind of much more important compared to the path costs. Now let us see that how we do such kind of inter-domain routing protocol. And predominantly in the internet, the protocol that is used for this kind of inter-domain routing is the Border Gateway Protocol, or BGP. Okay. So the initial protocol that was designed by ARPANET, which is called the Exterior Gateway Protocol, or EGP, that was designed for a specialized topology such as a tree topology. BGP then replaced EGP. The main change from EGP to BGP was that BGP generalizes the topology structure of the internet. It says that the internet need not to follow any kind of specific tree kind of hierarchy or something like that. There might be direct peering relationship, and BGP can adhere to those kind of peering relationship. BGP assumes that the internet is an arbitrary interconnection of a set of autonomous systems. Well, so here I'm not going to see about the routers or the individual hosts. I'm just going to see the autonomous systems as a whole. And we have two different type of traffic. As I was mentioning, we have the local traffic The local traffic means the traffic which originates or terminates on nodes within an autonomous system. And the transit traffic are basically the traffic that passes through an autonomous system. Okay. So typically, if I just go back to my previous diagram, so what actually happens, say, assume that ASJ wants to forward a packet from ASX to ASY, working like a transit traffic. So typically, the packet uses some kind of intra-domain routing protocol like RIP or OSPF to reach to this gateway, which is interconnecting ASX and ASJ. Then it again use the intra-domain routing protocol like the RIP or OSPF, which has been configured within ASJ, to forward it to the other gateway of the ASJ, which interconnects ASJ with ASY. Then it moves to the ASY. Okay. So that means you can think of it in a hierarchical way. So in one way, I'm saying that the path is from ASX to ASJ to ASY. Now, when the actual packet is forwarded, so whenever it is within ASX, it follows the routing protocol of ASX. So when it is moving from ASX to ASJ, it follows the routing protocol within ASJ. That is being configured by the network administrator of ASJ. Okay. Now, as we have already mentioned that there can be three different type of autonomous systems. The stub autonomous system, which only carry the local traffic, because they are not connected to multiple different autonomous systems. So they basically just get the data or put the data to the service providers. They work like a consumer or the producer of the network traffic. That way they carry the local traffic only. Then we have the multi-homed autonomous systems. This multi-homed autonomous systems again only carry the local traffic. It refuses to carry the transit traffic. So that means you are connected with multiple other autonomous systems, but you are just taking the traffic from one autonomous system or forwarding the traffic to another autonomous systems. You are not using any kind of transit traffic. Okay. The second picture, the middle picture here, it is an example of such kind of multi-home device. So you are making a connection between, say, this AS100 to AS200 or AS100 to AS300, but from 200 to 300, you are not forwarding the packet. Then we have the transit OS. The transit AS are by default a multi-home AS because they need to transit the traffic between two different autonomous systems. Okay, so they can carry both the transit traffic as well as the local traffic. Okay, now what are the objectives of BGP? So the objective of the BGPs are as follows. The first is that it provides the best non-looping or loop-free policy complaint path. Okay. So I need to find out a path which is free from any kind of routing loops, and at the same time it is complying the policies or following the policies of the individual autonomous systems. Okay. Then the second is the scaling. Now the CIDR at the internet scale may not be scalable, as I was mentioning earlier that. I think in the yesterday's class, one of you asked this question that if I need to prepare a routing table for the global internet based on CIDR, my size of the routing table is going to be huge. Well, so that way it is, that kind of idea is not scalable. Well, so if you just want to implement based on CIDR, then you need to store IP netmask information for millions of such subnets. Rather than doing that, what BGP does that it defines the path based on the AS number, not the IP. Okay. So what BGP does, it just follows a sequence of AS, like AS12, AS14, AS76, AS132, AS45, AS61. That basically means that if you want to forward a packet from AS12 to AS61, you can go via this order. You can forward it from AS12 to AS14. Then AS14 can forward it to AS76, then AS76 can forward it to the AS132, then AS132 can forward it to AS45, and finally AS45 can forward it to the AS61, which will take care of finally delivering the packet to the corresponding subnet based on its intra-domain routing protocol. Then comes the idea of the path cost. Now, this is something very interesting. Well, now, as I was mentioning earlier, that the autonomous systems are really autonomous. Well, so every individual network administrator might define the path cost within an autonomous system. Well, so that means one autonomous system might take the inverse of the network bandwidth as the path cost. Another autonomous system might take hop count as the path cost, the third autonomous systems might take the delay as the path cost. Well, now whenever I'm defining an end-to-end path, how I am going to define the path cost? Okay, because it is basically different metrics and you cannot just simply add defined metrics or subtract defined metrics to define the path cost. That is not possible. So because of such kind of problems, what the BGP does, that BGP simply forgets about the path cost. It doesn't bother about the path cost at all. So that I think I was mentioning some time back, that BGP just considered about the reachability information, whether a particular subnet is reachable via an autonomous system or not. Okay, so it does not think about what is going to be the optimal path to reach a particular subnet. If you can reach to that subnet, then it is fine. The individual cost minimization will be taken care of by the individual autonomous systems in that one. So that was the basic policy behind BGP, and that as a result, it might happen that you choose on a longest path rather than a shortest path, and we just accept that. Okay, because we do not have any other choice that can be performant and at the same time scalable. So as I was mentioning earlier, that there is always a trade-off between the correctness and the performance of the scalability. Okay, you cannot satisfy both in a large-scale network. You need to make a trade-off between the two, and the things we do here at the AS level, we do not bother about the path cost. We only bother about the path cost when the packet is forwarded within an AS, and that way our assumption is that, well, in the worst case, there might be one additional AS which might get added up, or some AS having a higher cost will get added up, but that will be kind of eventual. Okay, so it is not a kind of very generalized stuff. Okay, now let us discuss about what is this reachability information. So we are talking about this reachability for the last few minutes. Now this reachability things in BGP term, we call it as the network layer reachability information. What is that? So this is a autonomous system reachability information are basically shared by the BGP supported routers. We call them as the BGP peers. So if a router is supported with the BGP protocol, we call those routers as the BGP peers. Now this NLRI or network layer reachability information is shared between the BGP peers through the BGP update messages. Okay, so NLRI is nothing but an IPv4 prefix with the IPv4 protocol with the corresponding network IP. So one such NLRI information can be 110.12/16. So you can just see that this is a kind of network IP that I am providing, a kind of subnet IP that I am providing. Okay. So it is used to find out the AS reachability as well as the route aggregation through CIDR. So we see that if two subnets are, again, the way we did route aggregation for routing table construction, the same type of route aggregation we do here. We can actually see that if a same AS is providing reachability to multiple different autonomous systems and they can be combined based on CIDR, we combine them. Okay, so for example, you can combine 110.12/16 and 110.12.8/24 together to form 110.12/16. Right. So based on that CIDR aggregation mechanism. Okay. In the case that when both the subnets are connected to the same AS, so you do not need to maintain duplicate paths. Now there can be two different type of BGP supported routers, as I have mentioned earlier, that if a router supports BGP protocol, we call it as the BGP peers. So this BGP peers basically share the reachability information among themselves. There are some special type of BGP peers which actually produce this BGP update messages or the network layer reachability information. We call them as the BGP speakers. Okay. So a BGP speaker is a router that is configured with BGP, and it is a spokesperson for the entire autonomous system. So for example, within IIT Kharagpur network, we can designate one BGP supported router as a BGP speaker, and the task of that BGP speaker would be to announce the subnets which can be reachable via the IIT Kharagpur autonomous system. Okay. So once initialized, it uses the well-known BGP port like the TCP port 179 So BGP works on top of TCP to connect to other configured BGP peers in the internet and share the autonomous system reachability information. Now, this BGP speakers advertise the path information with the BGP speakers in the peer autonomous systems. So for example, IIT Kharagpur network is connected with the connected with the ARNet network. So the BGP speaker of IIT Kharagpur network will announce the BGP path information to the ARNet BGP speaker. Okay. Now let us see how a BGP path information looks like. Okay. Now BGP advertises the complete path information as an enumerated list of autonomous systems to reach a particular network. And here actually differs from our typical CIDR routing table. In case of CIDR routing table, if you remember, what information we have stored is the next hop information. We only put the next hop information, and when the packet is being forwarded to the next hop, we again decide that what is going to be the further next hop from that intermediate router, right? So that way, my typical CIDR routing table works. But in contrast, in case of BGP, we do not maintain that kind of next hop information. Rather, we maintain the entire path information. Why? Because in case of CIDR, I am running a routing protocol at the backend, and that particular routing protocol is ensuring the loop-free routing. Okay, so I am using Bellman-Ford algorithm or maybe Dijkstra's algorithm to find out the shortest path, either in the distributed version or in the centralized version. Distributed version in case of distance vector, centralized version in case of link state. But whatever protocol you are using, I am ensuring the link state. I am ensuring the loop-free routing. Okay, but in case of this BGP, where the autonomous system graph is huge, you cannot use any kind of such kind of shortest path algorithm that will ensure loop-free routing. Well, because of such kind of massive structure of the network. If every autonomous system starts learning about the other autonomous systems in the internet, then entire network bandwidth will get consumed only by the control packets. So that's why we cannot have that kind of luxury whenever we are talking about the autonomous systems interconnectivity and trying to find out the routing for the paths between multiple autonomous systems. And that is the reason we are not been able to use any kind of shortest path algorithm like Bellman-Ford's algorithm or the Dijkstra's algorithm. So the question comes that how I am going to apply or how I am going to ensure loop-free routing, because just a few minutes back we mentioned that loop-free routing was one of the major objectives behind the design of it. Now to maintain loop-free routing, BGP takes this policy that just rather than putting the next hop information, because we are not using any kind of standard graph theoretic algorithm to find out loop-free shortest path, let us apply or let us put the entire end-to-end path in the form of sequence of autonomous systems. Like the example I have shown you earlier, that AS1 to AS5 to AS8 to AS11. And that way, in this entire path information, if an AS comes to get twice, you can immediately identify that there is a loop. Okay, so that means you need to, whenever the network layer reachability information is being propagated in the network and you construct that AS path information, that AS path information should not consider the same autonomous system twice. Okay, so for example, you have started from AS1, you have moved to AS5, then you have moved to AS6, then you have moved to AS8. And then again, if you see that you have moved back to AS1, you consider that well, there is a routing loop and you discard that one. Okay, so that way the entire AS sequences are put in the path information. Now, this is also necessary to enable the sort of policy decisions. Okay, because I need to see that whether two autonomous systems can directly transfer traffic between each other based on their existing business policy or not. Well, say for example, this subnet 120.96 and 192.4.153 is connected with AS4. Now AS4, the BGP speaker of AS4 is basically broadcast that information that construct the NLRI packets and broadcast that network layer reachability information. It reaches to AS2, and then AS2 says that, well, I can reach 128.96 via the path AS2, AS4. Now it rebroadcasts again this NLRI information and reaches to AS1. Then AS1 constructs the path that, well, I can reach to 128.96 via AS1, AS2, and AS4. Okay, so that way I maintain this entire kind of AS path information. Well, similarly, this information is again broadcasted and it reaches to AS3, and AS3 finds out a path that, well, I need to reach to 128.96 via AS3 to AS1 to AS2 to AS4. So this entire path information is maintained here. Now, if you look at the BGP update message structure, in BGP update message structure, you have this field called path attribute. This AS path attribute actually contains this entire path. Okay. This example that I have shown you earlier. So every BGP speaker, when it receives an update message, it appends its own autonomous systems number in this AS path attribute value and advertise that to other BGP peers. Okay. And this length and prefix are the prefix information, that the NLRI information that are being appended within a BGP update message. So here is an example. Okay, so that will make the entire idea clear. So I have a network of autonomous systems. So AS10 to connected to AS51 to AS59 to AS138 to AS228 and to AS780. Okay. Now say this subnet 110.23/16 is connected with AS10, and 115.25/16 is also connected with AS10. So the BGP speaker of AS10 constructs an BGP update message. So in the BGP update message, AS path attribute contains the ID of this autonomous system, that is 10, and the corresponding NLRI informations are 110.22/16 and 111.25/16. Okay. Now this information gets propagated to AS51. When it reaches to AS51, 51 just appends its own path information in the AS path attribute, and it broadcasts it further. Then it received by AS59. Once it receives in 59, 59 again append its own AS number with the AS path attribute and broadcast it further. So it reaches to an AS138, AS138 append it. Then it gets reached to AS228, AS228 appends it, and finally it reaches to AS178 and AS782 and 782 appends it. So that means AS782, the BGP speaker of AS782 actually learns that if it wants to forward a packet to a subnet of 110.23/16, it needs to be forwarded from 782 to 228 to 138 to 59 to 51 to 10. Okay, so that is the sequence of AS that it needs to follow. And whenever the packet will be being forwarded, so it will be forwarded following this kind of BGP path information. So it will use the intra-domain routing protocol of say one machine within AS782 wants to forward a packet to the subnet 110.23. So that machine will generate the packet, and that packet will route it to the gateway router, which is BGP configured. And this forwarding will be done through some intra-domain routing protocol like OSPF or RIP. Then it will find out from this AS path information that, well, next I need to forward it to AS228, AS138 via AS228. So within AS228, from this gateway router to the gateway router to AS138, it will again use some RIP or OSPF to forward. And so once it reaches to AS228, again it will look into the BGP path information to find out next OS autonomous system where it needs to be forwarded. So that way the packet gets forwarded in the entire internet. Okay. Now, for BGP route establishment, so that is actually a very complicated algorithm. As I was mentioning, that it considers multiple different factors simultaneously. So based on the BGP update message, a BGP speaker may have multiple paths to a subnet. So it might receive multiple different NLRI, and based on that, it can have multiple different paths. So if you go to that right start page that I have shown you earlier, which contains the autonomous system information, there you can actually see the different broadcasted ASPAT information from different BGP speaker, and there you can see that, well, for a particular BGP speaker, there are multiple different paths which are available. Now the question comes that whenever a BGP supported router needs to forward a particular packet or decides about the next autonomous system where it wants to forward the packet, how will it decide? So it decides based on a complex algorithm that actually combines the different internet policies with other factors together, and it gives priority with different type of traffic. So for example, the local traffics are given priority over the transit traffic. And I have given you here in the slides the link where the entire algorithm is given that are being followed by the Cisco routers. And that particular Cisco algorithm, so if I just open it, so okay, so let me just share my desktop. Okay, so I hope my desktop page is visible to you. Any one of you, please respond. You can see that website page, right? The Cisco BGP page. Yeah. Okay. Good. So here you can see that it has actually given the rules which are being followed. Okay. So for example, prefer the path with the highest weight. Okay. So again, weight is a Cisco specific parameter. Well, it is local to the router on which it is configured. So you will see that many of such parameters are actually Cisco specific, and interestingly, different BGP routers they optimize it based on, although they follow the basic BGP protocol, but they use certain parameters which are specific to this particular hardware or the particular enterprise routers that you are using. Okay. Then the second rule says that you prefer the path with the largest local preference. Well, then your third rule is prefer the path that was locally originated via a network or aggregate BGP subcommand or through redistribution from an IGP. Well, so that means you give priority to the local paths over the say the transit routes. Then the fourth rule says that you prefer the path with the shortest AS path information. So if you have multiple AS path, then whichever is providing you the shortest path, you consider that one. Okay. So that way you will see that there is a set of rules which are there. Indeed, there is a set of 13 different rules. So based on those 13 different rules, you decide about that, or every BGP router, or at least the Cisco BGP routers can decide about which particular path to choose to forward that a packet over the autonomous systems using BGP. Okay, and certain examples are also given here, so you can just look into that to get an understanding of that. Okay. So I'm not going to this technical detail. This is just leaving you for your study because different routers, they use different such kind of algorithms. Although there are some basic rules like giving preference over the local path compared to the transit path, then giving preference to the shortest AS path. So that kind of rules are there, general rules which are being followed by all the different commercial routers. But typically, multiple commercial routers, they also put their own preference or their own rules while configuring the BGP path selection. So this gives you a kind of broad idea about the BGP protocol. Another thing I just wanted to show you. Just a minute. So there is something called a BGP looking glass. So this BGP looking glass is something a kind of public BGP database that is being maintained uh, by the RIPE Atlas. So you can actually look into this BGP looking glass to understand about how this AS path information looks like, and what are the different parameters which are there in the AS path information, and how the internet is actually you can construct even the internet graph with the help of that kind of looking glass information. Let me just load it. Okay. So the site is taking time to get loaded. Let me, I had a screenshot in the slide. Let me just show it from there. Okay. So if you just open this BGP Looking Glass, this particular link, you will see that it will provide you this different information about the BGP peers that has announced a path and this AS path information. So here I have just made a search for an IP 203.110.42.19. For this particular IP, this is actually one of the IP at IIT Kharagpur. So you can see that uh, this IP belongs to the autonomous system AS55847. This AS55847 is the autonomous system for IIT Kharagpur. So this AS55847, that is seen as the origin by 8 peers. That means 8 BGP peers that has found out a path to this AS55847, and these are the set of parts which are there. Okay, so some of the parts, not all, I have shown in the screenshot. So for example, AS6453 to 4755 to 98852 to 55824 to 55847. Well, so that way you can see the path information, and actually you can find out, or you can find out the details of this autonomous system to see that how the IIT Kharagpur network is actually connected and how it interconnects different ISPs globally to forward the packet. Okay, so that way actually you can, if you just play with that, you can construct possibly a nice graph where this IIT Kharagpur resides as a root, and you can find out the other parts through which this IIT Kharagpur autonomous systems can be reached. Okay. So this is all about BGP. Let me know if you have any questions or queries regarding BGP. Okay, so if not, then fine. So you can, I have uploaded the previous slide. I'm just going to upload this slide as well. So what I would suggest you that by this week you read this topic, two topics, the internet addressing and the routing, and try to play with the different tools that I have shown you, and such kind of like that. This route minus a in Linux machine, then this write BGP stack. So try to play with this kind of tools, and if you just try to explore this, I guess that would be the kind of best learning that you might have rather than just reading a lot of materials. Okay. So computer network is a system subject, and you can learn it best by exploring it yourself or making your hand dirty by exploiting these tools and trying to see what is actually happening or how your network is working. So one thing you can actually do, which that can be a kind of take-home assignment for all of you. It's like that you can just, so now every one of you is connected to different internet, right? Different subnet. Now you can just find out your subnet, find out what is your autonomous system, and find out all the parts that are being announced for that particular autonomous system. Okay, so that way you can actually explore that how you are connected to the global internet, and through which different subscribers you are actually receiving the internet. So for example, if you are now connected to the Airtel network, you can see that what is the autonomous system corresponds to the Airtel network and how it is connected to other network from where it is getting the service and all these details. Okay. So that way it will be a good learning experience for you, and you can that way also explore the different service providers which are available in India and how their network graphs looks like. Okay, and that would be a kind of interesting and joyful playing exercise. Okay, so I would suggest all of you to try that out with the help of this RightStart website, and that will be give you the best learning experience in this course. So if you face any difficulty or if you have any query, any doubt, anything, feel free to reach me or post your query on Teams chat. I would be happy to answer. Okay, so let me stop here today. We are at 9:57. So we are going to meet next week on Monday again. So we'll discuss about how a router looks like. Okay, so what are the different components of a router and how typically a router works. Okay, so that's all for today. Thank you all for attending the class. So see you on next Monday. Take care. Bye-bye.